I know it's not.
Okay, yeah, all right. So, yeah, so today's lecture sucks. I won't lie. Like, I've been reviewing it, and I'm just like, man, this really just sucks. So, we'll just probably stop and have a joke-telling session about halfway through, just to wake you all up, liven you all up.
We can look at the card pictures.
We can look at what?
The card pictures.
I'm gonna show those at some point, but not yet. Okay, so now actually we're going to, towards the end of the lecture, we're going to touch on something which you all know very well and you've used, but you might not have seen it proven. So if we get to it, we'll talk about something which you might find useful. Okay, but what I'm going to do is I'm going to start by talking about how having an orthonormal basis impacts determinants. So, that's a pretty strong magnet. Yeah, it's loud. Okay, so I want you to consider, oh man, this thing is dead already. Oh, this could really suck. I hope this black marker's not dead. It's close to dead. Who has a black marker? You see any black markers back there on the walls? No black markers.
This man has a black marker. I got blue. Stupid. He's already got blue.
Well, no, I mean, I can use blue. My blue is fine, but I usually write in black. But we're writing blue today. Yeah, I just hope to God blue shows up.
Oh, no.
Okay, all right. So, consider a matrix A, where we normally label the components of A as such. Okay? But we're going to take A to be something special. We're going to take A to be a matrix which is comprised of row vectors which are orthogonal to each other. Okay? So one way that we could label this is we could say this is A1, A2, to AN, where each of these row vectors has n components. Okay, so this is just a notation newbie, all right? There's nothing deep and profound in what I just said. But I just want you to bear in mind that I am saying something specific about this matrix. All the AIs are orthogonal. Okay, that's not a general result, but we're going to see what we can do with this. Okay. Now, clearly, we know that A times the adjoint of A is A times A starred transposed. Okay, that's the definition of the adjoint. And this, of course, is the multiplication of two matrices, and we know how that works. If I have the elements of A, and I can call those AIJs, and I have the elements of A star transpose, which I can call AJK star transpose, then matrix multiplication is basically summing over the second index from the first set of elements and the first index from the second set of elements. And then, of course, what you end up with after you do the summation over J is something indexed by I and K. Okay? Which is, of course, a matrix. All right? Now, what we can, of course, do, let me think. Well, these are just numbers, so I can certainly reverse their order, right? So for those of you who are not comfortable entirely with index notation, okay, whenever you're dealing with index notation, the beauty of it is that you can rearrange the order of things. Okay? Whereas, for example, you know, if you're doing, let me think. Let me think. come up with an example off the top of my head for some stupid reason. But at any rate, oh yeah. If you want to, okay, yeah. If you want to recast this in terms of multiplication of matrices, then this is A times A star transpose. You can't flip the order of the matrices because you'll get something different. But you can flip the order of these because these are just numbers. Okay? At any rate, we'll flip the order of them. All right. Pause. Oh, yeah. I want to transpose this. So I'm going to transpose this. So I'm going to reverse the kj. And that affects the transpose. Well, wait a minute. This is the sum over the second index. The second index is the column. So that's taking a vector here, which is labeled by k, another vector here, which is labeled by I, and it's saying take the inner product. Take the first components of each, multiply them together, add the second components of each, multiply together, da 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 da. Okay? So this is secretly just AK AI, which of course, since they're orthogonal, we know it's delta Ki times the magnitude of AI squared. Okay? They're not normalized, so the magnitude of AI is not necessarily 1, okay? But they're orthogonal. Okay? Now, so what we have is that A dagger is basically zeros everywhere else. Delta Ki is just the identity, in a sense. Okay? And therefore, of course, the determinant who did that? Is that automated?
Yeah. It's based on like the sunset, I think.
They let the shades down at sunset.
I don't know.
Or when it gets darker outside, when it gets darker in here.
They
probably brighten the lights and
Yeah.
Oh, yeah. Okay. All right. That's cool. What's the determinant of that matrix? Oh, let me get a name. Oh, there we go.
Sorry, one sec.
Do you not have the things printed out or on your computer? You're saying you can't read what's on the board? Don't give me that.
I can't. It's on the board, but I think you're saying that you want it to be the absolute value of A1 squared, A2 squared, etc. to A squared.
Yes, okay, good. Yeah, I mean, obviously this is the world's easiest determinant to take because it's a matrix of all zeros except the diagonals. So the determinant is just the product of the diagonals. Excellent work. Okay? And that's up to an squared. Now, that's a useful result for the product of a matrix of this special form with its adjoint. That's not very useful. What?
I'm just asking Dan a question, but I think it's a dumb one, so I don't want to ask you.
Oh, you can always ask me a dumb question. Those are the most fun. Ask me the question.
Is this for something over J on the line where you have, it's not the bottom line, but the middle line? Yeah, move all the way over to the right side. Why is it in AI? Keep going. Yeah, that one.
Well, these are orthogonal.
Mm-hmm.
So what are they? What do you get if if k is not equal to I.
0, yeah.
0,
Okay,
so that's what
because
the,
it's I and K, and when they're the same, you can just say it's I squared.
exactly,
Okay, cool.
yeah, that's it, exactum of it. Okay, so, oh, wait a minute. I bet you that we can take this and we can extract a powerful statement about this. Now, this is not the product of A with its adjoint. This is just A. Okay? I bet we can prove that this is equal to this. Let's do it. Ready? Here we go. Okay. So det A is just the determinant of A dagger star. Okay. It turns out that if you have a matrix and you take its determinant, oh, sorry. If I star this guy, then this turns just into a transpose, right? But isn't the determinant of the transpose of a matrix the same as the determinant of the matrix? Yeah, that's why these two are equal. Okay? Now, this tells me that det A star is equal to det A dagger, because if I star both sides of this, this becomes det A star, this just becomes det A dagger. Okay? And det AB, well, the determinant of the product of matrices is just the product of the determinants of them individually. So together these will tell us that the determinant of A dagger, is the determinant of A times the determinant of A dagger. But that means that this is the determinant of A times the determinant of A star. But that's what this is. Okay? I mean, the determinant of A can be a complex number, so you understand this. Oh, sorry. Pardon me. So this is the square root of this. Sorry about that. So det A, here, I'll clean it up. And phrase disappear. So det A, magnitude of det A, which is the magnitude of det A, magnitude of det A star. There you go. All right? Yes?
So why does the dagger become a star?
Why did the dagger become a star where?
The
Here?
bottom line. So that A dagger equals that A star.
In the row above, it's got the error.
So the det A dagger is det A transpose star.
Well, no, I see above that we set them equal to.
Uh-huh.
But if we want to show, no, I guess it's fine. I guess I'm just confused about why we make that change.
All we wanted to do was we wanted to remove the transpose part of the adjoint because the magnitude of det A is just det A times det A star. It's not times, but the transpose in this story just kind of, it disappears because the determinant doesn't care. Okay? All right. I mean, really, if you just squinted your eyes at this and said, well, who gives a shit about the transpose in there? It doesn't do anything to determinants. Then you could have actually just guessed this. Because you could have said, that's really just the complex conjugate that's actually playing a non-trivial role. These are just the details of that story played out. Okay? Now, it's going to get interesting. This is a special story. A is very special. It's made of a bunch of rows which are all orthogonal to each other. That is not a particularly general matrix form. So let's back the F up and talk about a more general matrix and see what we can do, okay? So I'm going to yeah, I'm going to erase the proof of this, but keep all the rest of it on the board. Okay, so now consider a matrix B. Okay, where again, I'm only going to assume that each of these is an n-component vector, but I'm not going to assume that they're orthogonal. Okay? So this is a general matrix. I mean, you can always take a matrix and say, I'm going to call each row a vector and label it by a single number, and then it's got n components, okay? You can always do that. All right. Now, okay, now, if I give you a list of vectors and they're not orthogonal, can you address that? How? Nope, I'm going to draw a card. Lucas, if I give you a set of vectors that are not orthogonal, what can you do to make them orthogonal?
Can I ask the question?
Yeah. You can Graham Schmidt the shit out of it. Yes. We're going to Graham Schmidt the shit out of this thing, okay? Now, trust me, if you have not looked at your homework assignment, you're going to get plenty of practice with Graham Schmitting things, okay? At any rate, we can always take these and we can transform them into a set of orthogonal vectors. So let's imagine doing that. So B is in the process going to become a matrix B prime, where the first vector will just be B1 over the magnitude of over the magnitude of B1. Remember, in the Graham-Schmidt process, you can pick any vector and just call it the first element of the orthogonal set, because a vector is orthogonal with itself. You know, if it gets into bed and plays with itself, it finds out, I'm orthogonal. Okay, but it's the next one, which is not going to be trivial. The next one will be B2. That's the second element, minus the inner product of B1 with it, times the basis B1 all over the magnitude of this bad boy. Okay, so remember, the spirit of Graham-Schmitting is we take a component. God dang, that's tough. We start out with a vector, and then we take the second vector, any vector that we want, and we subtract out all of the parts of this vector which are parallel to this vector. Okay? And that leaves in this entire term only components which are perpendicular to this. That is, they're orthogonal. All right? And then we just continue the process on down the chain. Good? Okay, so this thing is going to turn out to be exactly of this A variety that we started with. Everybody see that? It's now a set of orthogonal vectors if we Graham-Schmidt all the way down. Now I'm going to do something that's going to seem confusing at first. Now what I'm going to do is I'm going to define a matrix C. And the matrix C is going to be, and hold on, let me actually label these. Okay, so these, the elements of the vector elements of this are B1 prime, B2 prime. And then what I can do is I can define a matrix C, which is composed of the magnitudes of each of these vectors times the vectors. Okay?
Is that just unnormalizing it?
Well, what exactly is it doing? Yeah, it's unnormalizing it. So here, B1 cancels B1 in the denominator. Okay? So this element is just B1. However, the second element is multiplied by the normalization factor, so the denominator disappears, but I am left with the numerator. So this becomes B2 minus B1 over the magnitude of B1, producted with B2, B1 over the magnitude of B1. Okay? Everybody see that? Now, here's an interesting question, and it's a hard one. And fortunately, I'm going to get to ask Scott.
All right.
You ready?
Yeah.
And you so threw me with a damn mustache that you, well, actually, you could still have the mustache underneath that, but I've seen you on video enough to know you don't have the mustache anymore. Okay, here we go, Scott. You ready? I would argue that in this story, right here, the determinant of B is equal to the determinant of C. That is, the determinant of this is the same as the determinant of that. Can you support why that would be?
Well, first, contextual evidence. We probably wouldn't be talking about it if the answer was no.
It's true, it's true, it's true.
First thing, I feel like we're gonna take a complex conjugate and relate it back to A.
Nope.
Something like that. Okay.
Any other takers? This is where seeing through this dense notation to find something that you already knew can be so difficult. Yeah.
C is just a transformation of B, right?
Sorry, C is just a transformation of what?
B.
What kind of transformation of B is it?
It seems like one that's scaling out all of the magnitudes.
Wait, B is, no, C is orthogonal. Like each component is orthogonal, right? Not orthonormal.
Yeah.
And so isn't it the same argument as A now? Because it's orthogonal?
Well, is B orthogonal?
No, but
No,
C is.
it's not. C is, but B is not.
But you just said, oh, we're arguing that B equals
That B equals det C,
Right.
not that C equals B.
so close.
Yeah, no, that's fine.
So I remember back when we were talking about determinants, we had one property where you could add linear you could move the columns around as much as you wanted to.
Yeah.
So there, that's that.
Look at what we're doing to this to get this. We're taking the first row and we're not doing anything to it. But for the second row, we're adding a constant times the first row. All of this shit is a number. That thing right there is the first row. So to the second row, we're subtracting, but same difference. We're adding a constant times the first row. Well, for later elements, it would always be the original element of B, and then you add in constants times other rows. If that's what you're doing to your matrix, is just taking a row and adding it to another row, or a constant times it to another row, that doesn't change the determinant. You've seen that. Okay? So we have that the determinant of B equals the determinant of C. Now, well, C is a matrix of these magnitudes times these vectors. But what can you tell me about these vectors?
They're terrifying vectors.
They're what?
They're terrifying, but they're orthogonal.
They're not just orthogonal,
Orthonormal.
they're orthonormal. Exactamundo. Okay? So at the end of the day, C is composed of vectors. I gotta make sure I get this right. Orthonormal vectors, C1, C1, times scalar multiples. So C, yeah. Okay, so C is composed of orthonormal vectors, those are the B primes, I'll just call them C's, times these coefficients. And then if we do determinant of C, we end up with nothing but a product over all of those coefficients, because the C1, C2 vectors are all orthonormal. Okay? Well, how is a BI related to a BI? So the betas are these coefficients. This is simple, this is complicated, but nonetheless, how is this related to B2? Is it equal? Well, how is beta 1 related to B1? Yeah, so beta 1 is equal to B1. Okay, their magnitude is the same. What about B2 and beta 2? Okay, so beta 2 is B2 minus B1 over B1.
It's smaller.
Yeah, it's smaller.
Okay.
Okay? So what we find is that the betas are smaller or equal to the B's. All right? And this leads us to an inequality, which is called a Hadamard's inequality. And Hadamard's inequality basically says that if I take the determinant of an arbitrary matrix, then the magnitude of the determinant is less than or equal to the product of all of these normalizing factors. Okay? Remember, if A starts out in this special form where all of the vectors are already orthogonal, then it's equal. Okay? But it turns out that there's an inequality satisfied by an arbitrary matrix. All right? Any questions about that? No questions? Okay, I told you it's going to be terrible today. All right. Now, what we're going to do is we are going to, we're going to give adjoints a definition beyond the matrix definition. And then we'll link the two. We'll show how they're actually defining the same damn thing. And then we will turn to special operators, a certain type of which I know you're all very familiar with, but in due time. So, recall the definition of an adjoint matrix. Okay, which is largely what I've been playing with already. So A with elements Aij gives rise to the adjoint A dagger with elements A dagger Ij being the complex conjugate of the transposed element of the original matrix A. Okay? And we have some nice properties of adjoint matrices. If A dagger equals B, then of course A equals B dagger. And if I dagger a dagger, I get nothing. Daggering the sum gives me the sum of the daggers, and daggering a product gives me reversed order product of the daggers. Okay? Now what I want to do, so this is all what we're familiar with from matrix land. Now remember, and I've told you this story before, every linear operator can be isomorphically mapped to a matrix. Okay? You can then define properties based on the matrix representation, but you should also be able to define the properties just in terms of linear operators without necessarily relying on the isomorphism to matrix representation. So what could the definition of an adjoint operator be? Well, let's see. So let A be a linear transformation on a vector space. For every A, the operator A dagger, such that, and here we go, AX Y is X A dagger Y. For every X and Y on V, is called the adjoint. Okay? Now, first of all, notice we actually defined the adjoint in matrix land without utilizing an inner product. In fact, we defined the adjoint of an operator back before we even introduced inner products. Okay? But we're going to work with the definition now in terms of the inner product. And we can see where this takes us. So first of all, there's a couple of immediate consequences of this. For any A, there always exists an A dagger. There always exists an adjoint operator, okay? And for a given A, the A dagger is always unique. It's not like you have a choice of A daggers. You just have one A dagger. Moreover, the adjoint operator is also a linear operator. If A is a linear operator, then A dagger is a linear operator, so it satisfies all the requirements of a linear operator. All right? So some more features which we find are A plus B dagger equals A dagger plus B dagger, and these are going to mirror those. Right? Now, one could argue that all of these follow from this definition without recourse to matrix land. Okay, so let's see an example. Okay, so to prove one, we can, so to prove property one, we can start with this definition. X C dagger Y equals C X Y. Okay? This is just using the definition of the adjoint of C. All right? Now, let's take C to be the sum of two linear operators A plus B. Okay, plugging that into this expression, what I find is the following. Okay? We on board? It's pretty simple. I'm just replacing C with A plus B. Now, this is using the linearity of operators. I'm not going to use any matrix language. This is just due to the fact that A plus B are linear operators. So they distribute themselves based on what they're acting upon. This is based on the linearity of the inner product. If I'm taking the inner product of the sum of two things with a third thing, then this is just the inner product of the first times the second, or the first times the third and the second times the third. Okay? Now let's use the definition of the adjoint. Okay? And now let's undo the linearity of the inner product. Okay? Now, does this mean one second. Oh, damn. Okay, well, I'll do it now. Does this mean that A plus B dagger equals A dagger plus B dagger? let's say, okay, I mean, you're right, but let me explain it. So first of all, so this is equal to this. And, you know, your friend might be like, oh, that means that this is equal to this. That's so easy. And then you go, well, what if y was 0? If y was 0, this would be 0, this would be 0. But that doesn't mean these things have to be the same. They're just being multiplied by 0. Okay? Or better still, what if these things are projecting y onto separate subspaces which are orthogonal to x? Okay? That means that the inner product is going to be 0 even though this thing is not 0. Okay? I mean, that's like saying, you know, what I'm trying to say is like if I take the x-axis and I take the inner product with the y-axis, that's equal to the x-axis times the inner product with the z-axis. Does this mean y is equal to z? Shit, no, they're just both equal to 0. It doesn't mean they're the same, okay? However, as Joel just dispensed, all of this is taking certain cases of x and y into consideration. So what we can say is, yes, if it holds for all x and y's. So you can take any two vectors in the vector space, and if these are equal, then it's true. Okay? All right. Now there was a theorem that I had written down on my first thing, and I'm going to go ahead and throw it up on the board because it'll play a powerful role. And it actually plays into this story. A linear transformation A on an inner product space is 0 if and only if x, a, y is 0 for all x and y. Yes.
Can we have jokes in?
Sorry, say it again?
Can we have jokes in?
Yes.
Amazing, thank you.
Okay, go for it.
What did the janitor yell when he jumped out of the closet?
What did the janitor yell when he jumped out of the closet?
Supplies!
Supplies?
Supplies, yeah.
Supplies, that's funny.
Like you try to go back to class.
Oh, I can't.
Does anyone have a better joke?
That joke is actually funny though.
I thought it was pretty good. I mean, I thought it was pretty good. You gotta really just deliver those jokes to break through the somberness of the crowd. So, you know, that's why Avery was keen. Anybody else got a joke? No one's got jokes?
You got a joke?
Man, they went with my memory. I knew so many funny jokes, and now I don't remember a damn one. But I feel like that's been a limitation throughout my life. Like, I'm like, oh yeah, this joke is, what joke? I don't remember the joke, shit. But it's really funny. I made everybody laugh. Anyway, next time I'll come with a joke. All right, you're welcome. Can we get back to lecture now? Yeah, we have to do it. Okay, so, yes, okay. All right. So, yes. Okay. Does this mean, yeah, so one thing that we can do is we can tie this result into this result, because after all, if we take this statement and we just consider this minus this, that's A plus B dagger minus, we do this. Okay, and now we're just reducing it to this. Because if this is equal to 0 for all x and y, then this thing is 0, which means that A plus B dagger is A dagger plus B dagger. Okay? All right. I also, in one line, do the proof of this as well, but I'm not going to write that up on the board. Okay. I know I'm going to regret erasing this, but that's fine. I promise you, I think, we might not, I don't know, but I hope we get to something sexy before the end of class. But, you know, time runs out. And if not today, then next time. Okay. All right. So what is the connection between the definition of a matrix and the definition of a linear operator? Let the matrix A have components Aij with respect to an orthonormal basis x. Then A dagger with respect to the same basis x is A dagger Ij, which is Aj I star. Okay? Yes. Now let's prove this. So the basis x is going to be composed of orthonormal vectors. So we have that Aij is by definition the inner product of one of those with A acting on another. Okay, you might or might not recall this. We talked about this last time. But then Aij can be written as, well, we use the definition of the adjoint of A. Okay? And now, remember that the inner product of A and B is the complex conjugate of the reversed inner product. This is true for any inner product. It's obviously true if everything's real because the star doesn't do anything and AB is BA. Okay? But the star takes care of that you only star the first components, or the components of the first term in the inner product if it's complex. But that means that we can take this and we can reverse it. And so this is going to be xj A dagger xi starred. Okay? But this is the definition of the j ith component of the operator A dagger star. But this just tells me that taking these two and putting them together, A dagger Ji is Aij star. Okay? Which is what I promised you there. So again, I'm not using matrix language to show this. I'm just using the definition of an adjoint operator. Okay? I'm not appealing to any matrix language. Okay. I mean, one of the things that you'll notice when I am using purely the operator language and I'm not appealing to matrices, this entire story has no mention or reference to transpose. You transpose a matrix. The transposition of a linear operator is not well defined. But you don't need it. Okay? All right. Now, with the clear definition of adjoint in mind, it is now time to introduce a special class of operators. And this is where many of you might have been waiting. If A is equal to a dagger, then A is what? Thank you. A is self-adjoint. Okay? And you might be laughing. Of course, this includes Hermitian, but it also includes another case. If you are working on a real inner product space, then self-adjoint equals symmetric. That is, A equals A transpose. Okay? If, of course, you're working on a complex inner product space, then adjoint equals Hermitian. Okay? So now, let's focus on Hermitian operators for a moment and write down some important properties. All of these are the results of theorems which can be derived from this definition. If A and B are self-adjoint, so is A plus B. Okay? Obviously, to prove this, we can just take A plus B dagger, A dagger plus B dagger. They're self-adjoint, so this is just A plus B. Which is just A plus B. Okay? So the sum is self-adjoint. I think this kind of proof is the one where you're just sitting there looking at it and you're kind of like, that's obvious, that's obvious, that's obvious. That was a proof? Was that really a proof? But we're using properties, we're using linearity of the adjointing. We're using self-adjoints on individual terms to prove that the sum of two terms adjoint is the same as the sum of two terms if the individual terms are self-adjoint. Okay? If A is self-adjoint, then so is alpha A for a real coefficient alpha. Obviously, alpha A dagger, well, this is complex conjugate transpose that you don't transpose alpha, it's just a number, so it just gets a complex conjugation. But if A is self-adjoint, that's equal to that. And you want this to be equal to what you started with, and that's only true if alpha star is equal to alpha, that is, if alpha is real. Okay? And then last but not least, if A and B are self-adjoint, then AB is self-adjoint. If AB equals 0. Okay?
Does that mean A and B are 0 or the interval?
No, this is the commutator. It just means that the order in which you multiply them doesn't matter. Okay. So let's see if we can prove this third one. All right. So let's do if first. Assuming they commute, that is, this is an if, which means that if this is true, this is true. Yeah, this is true. But it also means that if this is true, then this is true. So we're going to start with if AB commute, then AB is self-adjoint, if AB are individually self-adjoint. So here we go. AB dagger is B dagger, A dagger. They're self-adjoint individually, so that's just BA. But if they commute, that's just AB. Okay? So what we just showed is that if they commute, then AB dagger is equal to AB. That is, the product AB is self-adjoint. Again, this is one of those which you look at it and you say, is he really doing anything? If A and B are separately self-adjoint, it is not immediately obvious that their product is self-adjoint, but we just demonstrated that it is. Only if you can reverse the order of A and B. They commute. Okay? And now let's do the only if direction. Assuming that AB, that the product is itself self-adjoint, then we have that AB is equal to AB dagger. That's the statement that you're starting with. But this is B dagger, A dagger. They're self-adjoint. So that's BA. And of course, what you just demonstrated is that they do in fact commute. Okay? Are you on board? Good? Good. This is excellent. Okay, so I'm going to try and get this slide done in 15 minutes. Yeah. Okay, so I am going to, I don't know how many of you are actually reading the book, but I am going to take a section of the book and I'm going to radically redo it in the discussion I'm about to present to you. So, but I think my discussion is going to make a little bit more sense than what is presented in the book. So here we go. Oh. All right. Now, I want you to remember the theorem that I wrote down here, and I'm going to write it up here, because it's going to be in comparison to other things. A linear transformation, A, on an inner product space is 0 if x, a, y equals 0 for all x and y. Okay? That was a theorem we talked about earlier. Now, it turns out that in certain situations, this can be strengthened. Let me give you the first strengthening. If A is a self-adjoint, linear transformation, in a real inner product space, then A equals 0 if and only if XAX equals 0 for all x. Okay? Now, why is that stronger?
We don't have to deal with y anymore, so you only have to deal with.
Right, here, so notice this is XAY, this is XAX. So imagine you have a vector space that's got a bunch of vectors. In order, in general, to show that an operator is 0, you have to show that its inner product of any vector with the operator acting on any other vector has to vanish. However, given these conditions, the operator vanishes if you only have a 0 inner product between a vector and the operator acting on the same vector. Okay? I don't have to worry about x and y where x and y are different. Okay? Now I'm going to prove these, but let me go ahead and add in one more. And this is perhaps the most amazing. If A is any linear transformation, in a complex inner product space, then A equals 0 if XAX equals 0 for all x.
Not if and only if.
Sorry, yeah, no, it's if.
Oh, okay.
You said it was surprising, so I just
Huh?
took you at your word.
Did I only said if
Yeah.
and I didn't say if?
You didn't say if.
I thought it.
Oh,
Okay, so first of all, let me give you some nameage to these. So if you're dealing with an inner product space, this is also referred to as a Euclidean space. Whereas a complex inner product space is called a unitary space. So I might interchange those words throughout. If I refer to unitary, then I'm talking about a complex space. A complex inner product space. If I mention Euclidean, I'm referring to a real inner product space. Okay? This is amazing because in the third one, we're not requiring A to be self-adjoint. We're simply saying that if A acts on a complex inner product space, then you get this same strengthening of the condition, that you only have to consider a vector inner producted with the operator acting on the same vector. Yes?
Can x be 0 vector? Because then that would be 0 no matter what.
X can be the 0 vector, but it's got to be true for all x. So that's what saves you. If this said any x, then you're screwed, because you could take x to be 0, in which case that's trivial. But no, it's all x, which includes the 0 and others. Okay? So here we go. So I'm going to start with a and I'll call this 1, 2, and 3. I'm going to start with the necessary condition for all three of them together, and then we'll prove sufficiency in each case. So to prove the necessity, first, obviously, if A equals 0, then x, a, y equals 0 for all x and y, including, of course, x equals y. Okay? So remember, this is if, so we want to show that this implies this, but more importantly, this implies this. Okay? Now, to prove the sufficiency, let's start with case 1. And here's our argument. If x, a, y equals 0 for all x and y, then we can take x to be a y. Okay? We can just say if this is true for all x and y, I can pick the x that I get when I act on a y with the transformation A. Remember that acting on a vector with a linear transformation gives you back another vector in the same space. Okay? So I'm just going to pick the special combination that x is a y, in which case we now have a y equals 0. This implies that a y equals 0. Okay, remember the rules that define an inner product? The inner product is only 0. The inner product of a vector with itself is 0 if the vector is 0. That's part of the definition of an inner product. Okay? This is true for all y. Therefore, a equals 0. If this is true for all y, including y equals 0, but also including y not equals to 0, then that means that a is 0. Okay? So what we just demonstrated was the sufficiency of this guy. That is, if we assume this, then we proved that the linear operator is 0. Everybody on board? Now let's go to case 2. What we're going to do is we're going to show that in the second case, the situation that we're talking about here actually reduces to this situation, although it's not obvious at first how that's the case. So here we go. If xax equals 0, for all x, then consider the following. Okay? X plus y is just a vector, and that's the same vector. So this is written of this form. Okay? But we can break it up because of the linearity of both the inner product and linear transformations. Okay? Everybody on board? Okay, look at it. we're going to start with this being true. If I have the same vector x and I'm acting on it with a linear operator, the inner product of those is 0. This is 0. What is this? 0. What is this? 0. Okay? So what we are left with is that xay plus yax must be 0. Okay? Now here we go. I'll put it over here. Let's have some room. But remember, yax, that's this guy right here, is equal to axy star. That's just the definition of the inner product. I can reverse the order as long as I complex conjugate it. Okay. And then I can use the definition of the conjugate, or of the adjoint. And then last but not least, we'll use that, in this case, A is self-adjoint. Okay? Oh, sorry, I missed writing one in. The complex conjugate of this is equal to the inner product without the complex conjugate. Why? Because you're in a real inner product space. Okay, and then I just use the definition of the adjoint to get here. Okay? But of course, together, these imply that, well, this is just xay. Okay? But this means that if this is true for all x and y, then A is 0. But that's a condition that is obviously true. Okay? On board? All right, so for 3, very quickly, if xax equals 0, then following what we did here, because we can do the same story here, I didn't use the self-adjoint property until right here. So all of this story holds in both the 2 and the 3 cases. So we can say that xay plus yax equals 0 for all x and y. All right. Now, since this is a complex space, what we can do is we can say, all right, I'm going to take y to be imaginary. I mean, I can do that. If I do that, then what I have is the following. X a I y plus I y a x equals 0. All right? Now recall that if I have alpha x beta y, then this is alpha star beta xy. because of that complex conjugation that you put on the first term in an inner product. Okay? So we have, oh my goodness. I recommend you guys never get old, because squatting down really hurts. Thank you for laughing. It was a joke. Squatting down never hurts. Feels good. Okay? I'm kidding. Where all I did was I used the fact that if I pull the I out of here, I've got a complex conjugated. That's where the minus sign came from. Here I'm pulling the I out of the second term. I don't complex conjugate. Okay? Looking pretty good. All right? Well, this is I times x a y minus y a x equals 0, which of course means that that equals 0. You agree? Well, look at this. This is 0, and this is 0. Let me draw a card. Max. Max. What do I get if I add 0 plus 0? 0. Damn! What if I add this plus this? What if I add this plus this?
0.
It's equal to 0, but what's the other side?
What's the what, sorry?
What's the other side? I add this to this. You get 2xay. Yeah, okay, so this entire story goes down to 2xay equals 0 for all x and y. Okay? This, of course, implies equals 0. All right? Now I'm going to stop there. When we pick up next time, we will begin exploring the properties of Hermitian matrices. These should be very familiar to you from your working quantum mechanics. If not, get ready to learn something or another. But remember, you do have a homework quiz on Thursday. I am going to add 2 more questions to the assignment tonight. I'll have office hours from 7 to 9 tonight, and then from 6 to 7:30 tomorrow night, and 1 to 3 in the afternoon on Thursday. So if you need help, by all means, drop in the Zoom room and get it.
Yeah, there's nails in them.
I think I've looked at my map.